Okay, we're now on question 13 of this paper, and this is a super tricky one. Not an easy question, this one. So this one, the level of difficulty has jumped up significantly, and I think in fact the part A is harder than the part B in this question. So it says, given that A is a positive constant, use the substitution x is equal to a sine squared theta to show that expression there. Okay, so let's think about what are our standard approaches, what are our standard elements, what are the things that we know that we should be doing in order to solve this kind of question. So the first thing we need to do is we need to be taking our x expression and differentiating it, okay? So we're going to differentiate our x. So therefore, dx by d theta, we're going to use the chain rule, okay? So our outer function is something squared. Our inner function is sine theta. Because remember, sine squared theta, when it's written like that, it means this, sine theta squared, okay? So using the chain rule, we're going to differentiate the outer one. So it's going to go to 2 times sine theta to the 1. And then we're going to times by the derivative of the inner function, and sine differentiates into cos. So that's quite nice. So that's the first thing we need to do. The next thing is let's get changing the limits out of the way. And this, I think, is one of the most awkward and tricky bits in this whole question. So our limits for x are a and 0. And we want to use this to work out what our theta limits are. So the substitution is x is equal to a sine squared theta. So what I'm going to do is I'm going to rearrange this to make theta the subject. So I've divided by a and square rooted it. Okay, so I've got the square root of x over a is sine theta. And then when I do the inverse of that, I get that theta is equal to the inverse or arcsine of root of x over a. Okay, so that's what we're going to be using to find our theta. So let's find out what theta is when x is a. A bit disconcerting the way it's algebra, but hopefully it's going to drop out nicely. So when x is a, x gets replaced by a, which is actually really nice because you end up with a over a, which is 1, and the square root of 1 is 1, and inverse of sine of 1 is arcsine of 1 is pi over 2, because the graph of sine looks like this, and there we are at 1 when we're at pi over 2. So therefore we've got that when x is equal to a, theta is pi over 2. So that's our first limit changed. Now let's think about what happens when x is 0. So when x is 0, subbing into our formula, we have 0 for x over a. Well, 0 over a is 0, and arcsine of 0 is 0 because sine starts off at 0. So when x is 0, theta is also 0. So we've changed our limits. But I think that that's quite awkward, the way you've got to rearrange that whole thing to get this cumbersome thing, and then you've got to sub-algebra into it. Not nice at all. But nonetheless, we've changed our limits. So now it's the main body of this question. It's time to sub everything in. So let's write down our original thing. We're integrating between 0 and a of x squared times the square root of a minus x dx. So that's our original thing, okay? Well, we've already done the limits. We know that they change into pi over 2 and 0. So that's taken care of there and there. X squared, we're just going to sub that in. X to the half, I'm sorry. We're just going to sub that in. So therefore, we replace that with a times by sine squared theta to the power of a half, because x is a sine squared theta. So we've subbed that in. And then here, we're going to have a minus x. Remember, our x is a sine squared theta. So I've just replaced that there. And coming back to our dx by d theta, our dx by d theta was a times 2 sine theta cos theta. Now, that means that when we separate the variables, it means that dx is going to be replaced by 2a sine theta cos theta d theta. Okay, so separating the variables, dx gets replaced by that. So our dx has now been replaced by that, the 2a sine theta cos theta, as just discussed, okay? So we've put all of the various elements in, so it's time to start doing some algebraic manipulation and tidying things up. So a to the power of a half, I've just removed that and written that as a to the half. The square root of sine squared is just sine. So that's that one done as well. Here, I'm going to take out a common factor of a, because that's looking suspiciously like 1 minus sine squared. So when I take out a factor of a, I've got 1 minus sine squared. And 1 minus sine squared is cos squared. So we've got the square root here of cos squared theta times by the square root of a. So the square root of cos squared is just cos. Okay, so this whole thing here simplifies into root a times cos theta. Okay, so far we've got root a sine theta and root a cos theta. So all of that has been simplified. Now, this is something that you'll notice that in the question, the thing we're aiming for in this question on the right hand side, we're aiming for sine squared 2 theta. So somehow we need to be getting 2 theta into this. And we've got to remember that our identity is that sine 2 theta is actually equal to 2 sine theta cos theta. Okay, so 2 sine theta cos theta. So we're going to replace 2 sine theta cos theta with sine 2 theta. Okay, so therefore our 2a sine theta cos theta has become now just a times by sine 2 theta. So we've got a times by sine 2 theta. Okay, good. So all of the elements have been replaced now. So let's try and do some further simplification. So what have we got? Root a times root a is a, times another a is a squared. Okay, so that one, and that one becomes a squared. We have got our sine squared 2 theta. Let's just leave that alone. So just write that down again. But notice we've got another sine theta cos theta. And actually, we're looking for, the thing we're aiming for in the question is sine squared 2 theta. So we've got 1 2 theta, but we're rather hoping to get another sine 2 theta. So what I've done is I've kind of engineered the 2 that I would need. So I've got sine theta cos theta, but I really want it to be 2 sine theta cos theta so that I can change it into sine 2 theta. So I've reverse engineered it. I've made a 2 there. I've conjured it up out of thin air. But to compensate, I've put a half outside the integral. Okay, so I've basically put the 2 that I need there, but to compensate for that, I've put a half outside the integral. So now that I've got my 2 sine theta cos theta, I can replace that with sine 2 theta. Okay, but I just need to remember that I've got a half outside that integral now. So I've now got sine squared 2 theta times sine 2 theta, which is sine squared 2 theta. But I've got a half and I've got my a squared. So that's exactly what the question was asking us to derive. So we've completed that first part of the question. Now, as I say, I do not think that was at all easy. Definitely a big jump up in terms of level of difficulty compared to how this paper's been so far. So that's quite a tricky, definitely a tricky substitution question for part A. Let's hope that part B is somewhat nicer. Part B then. We basically just got to work out what the integral is now, okay, and show that it is equal to k times pi times a squared. So there's our original integral. Remember, we know that the a is pi over 2 and the 0 stayed as 0, and we're integrating this. Now, funnily enough, I was just looking at this with one of my year 13 groups. In fact, both of my year 13 groups this week, we've been looking at this. And I've been saying that it comes up, this idea comes up in some of these really difficult kind of like integration substitution questions at the end of a paper. And lo and behold, here it is. So yes, what we need to do is we cannot integrate sine squared theta. Okay, you cannot integrate sine squared theta rather by using the chain rule backwards. That's what I mean to say. So we cannot use the reverse chain rule. And the reason is you can only use the chain rule backwards on something that could have come from the chain rule in the first place. And sine squared 2 theta could not have come from the chain rule. So we need to find an alternative approach. And the alternative approach is we use the identity we use the identity that cos 2 theta is equal to cos squared minus sine squared. Okay, so you would need to just go to the formula booklet, look at your cos. You'd say cos 2 theta is cos squared minus sine squared. Okay, then because we're aiming to replace everything here with sine squared, you would replace this cos squared with 1 minus sine squared, giving you 1 minus sine squared minus sine squared. So you now get that cos 2 theta is equal to 1 minus 2 lots of sine squared. Okay, and then when you rearrange that in order to make the sine squared the subject, you end up with a half minus a half cos 2 theta. But because we've got 2 theta here, it becomes 4 theta. Okay, I feel like, you know what, I'm doing too many steps in one go there for some people. So let me just put some extra steps in. So at the moment, we're just finding out how on earth am I going to change this sine squared 2 theta. Okay, so we're saying that we need to use the identity cos 2 theta equals cos squared minus sine squared. And we're saying that cos 2 theta is 1 minus sine squared theta minus sine squared theta. So in other words, cos 2 theta is equal to 1 minus 2 lots of sine squared theta. So I'm going to add that sine squared theta over to the left-hand side and take that over to the right-hand side. So 2 sine squared theta is equal to 1 minus cos 2 theta. Now I divide by 2. So sine squared theta is equal to a half minus a half cos 2 theta. Now you don't have to derive that. I've just derived this whole thing from first principles. You don't need to do that. If you can remember this identity, you can just use it directly. Okay, so there's not extra marks for deriving this. You can use this directly. So that's sine squared theta is a half minus a half cos 2 theta. Now what that means is that sine squared 2 theta is going to be a half minus a half cos 4 theta, okay? Because notice you've got theta there but 2 theta here. So if we've got 2 theta, we're going to need 4 theta there, okay? So that's what's happened. I've replaced sine squared 2 theta with a half minus a half cos 4 theta. That's where that's come from, okay? Just in case you were wondering, there's all of the supplementary steps that are required. Okay, so, but you could just remember that and sub it in directly. That would be okay. So we've now got to, this is what we're integrating, and this is all good now because we can use the chain rule backwards to integrate that, no problem, the reverse chain rule. So integrating a half with respect to theta becomes theta over 2. Using the chain rule backwards, we're going to say the outer function, integrate the outer function and divide by the derivative of the inner. So cos integrates to sine, and we divide by the derivative of 4 theta, which is 4. So you're going to get 1/8 sine 4 theta using the chain rule backwards. So we put our limits in, and the limits are pi over 2 and 0. So we've got pi over 2 minus 1/8 sine times by 4 pi over 2. Pi over 2 is pi over 4. And 4 times by pi over 2 is 2 pi. And sine of 2 pi is 0. So that bit is 0. It just kind of disappears. That bit's gone because you've got 0 over 2 and sine of 0. So that is gone. So we're just left with this little bit here. So we end up with a half a squared times pi over 4, which is 1/8 a squared pi, or to put it in the correct order for the question, 1/8 pi a squared. So therefore k is equal to 1/8. Now that certainly was not easy, but I hope that you found that useful, and I will see you in the next video.